All right, so thank you everybody online and especially in person for attending Samantha's talk today. Just a little bit of background before we get started on Samantha. She received her Bachelor of Science in Meteorology and Marine Science from the University of Miami in 2018. She is currently a PhD student in the Ocean Science Department and is advised by Roland Rohrmeister and Hans Graver. Her research interests include internal solitary wave amplitude and velocity retrieval from synthetic aperture radar images. And today she'll be talking about the effects of oceanic internal waves on momentum flux at the Air-Sea interface. And some of you might recall this talk was actually planned for a couple of weeks ago. So unfortunately we have to, do this during spring break, but hopefully we still have a lot of people in the audience, and also hopefully we will see a bunch of you on YouTube as well. So with that, I will give Samantha the floor.
Thank you, Haley, for that introduction. So today, as Haley said, I'll be talking about internal waves and their impact on momentum flux. And this work is related to the Coastal Land Air-Sea Interaction project funded by the Office of Naval Research. This talk will combine analysis of remote sensing data as well as in situ measurements. Just to touch on my previous work, which led me to this talk today, I initially began my work as a student here working on the California Inner Shelf project. So from this project, we actually acquired some unique pairs of satellite images from the Cosmos SkyMed satellite constellation, which has 4 satellites in the same orbital plane, and they have the ability to acquire both right and left looking images, which allows us to acquire these unique pairs of images separated by 24 minutes. So this is an example of one of those pairs here, and I actually was working on and developed a technique to estimate the phase speed and direction of these internal waves automatically from these pairs of images. So I'm just going to show an example here. So this is one image followed by a second image separated 24 minutes apart, and I'm able to derive motion vectors with the median speed and direction being the yellow vector. So this was what got me into my study on internal waves, and from that this led me to my current work looking at kind of a different perspective on internal waves than what I had originally started. So with that, I'll get to the main discussion of this talk. So I'm going to cover some background and motivation related to this, help you better understand what I'm talking about in this talk. I'm going to introduce the Coastal Land Air-Sea Interaction project and the data related to this experiment, and I'll be referring to this as Class C. Then I'll go through my data analysis methods and discuss my findings. So internal waves, if you're not familiar, are subsurface waves that propagate along the picnic line in the ocean. The ones that I will be talking about today are typically tidally driven. So the way these form is, considering a 2-layer ocean with an upper layer and a higher density lower layer, during ebb tide, when the tide is flowing away from the coast, the higher density lower layer will dip down when it encounters the continental shelf and form a U-shaped like depression along the interface. During slack tide, this will lift up a bit and it will slowly start to propagate back towards shore. And once the tides shift to flood tide, this feature will begin to oscillate like a wave, with the largest wave leading the packet, and accelerate until it eventually breaks. Internal waves are typically thought to be important for ocean mixing and energy transfer within the ocean, and have not been well studied in terms of their impact on the atmosphere. I mentioned that I will be looking at some remote sensing data today as well, so I'm going to cover how we can see these internal waves with synthetic aperture radar as well as X-band marine radar. So SAR only senses, or radar only senses the top millimeters of the ocean surface, which these internal waves propagate much lower in the water than that. So how can we see them? So internal waves actually modulate the surface currents. So the leading edge of the internal wave produces convergence of the surface current and a rougher ocean surface. creating a bright radar return. So you can see the brighter radar return in this image over here. And the trailing edge produces divergence of the surface currents and a smoother sea state, and therefore a dark radar return. So typically these internal waves show up in radar images as alternating bands of bright and dark. Just a little bit about momentum transfer and how we typically think about it. So we know the wind blows over the ocean surface and acts on the water surface, helping to develop these short gravity and capillary waves. And the wind transfers momentum to the waves, and these waves will eventually break and drive momentum downward into the upper layer of the ocean, creating this vertical exchange of momentum across the interface. And it's a well-known relationship between the momentum flux and the roughness length of the ocean, which internal waves also impact the surface roughness. So that's kind of what led me to this idea. So this is often measured in the field using a sonic anemometer, which measures the 3 components of wind velocity. And wind stress is a very important mechanism in understanding the air-sea interaction dynamics. So the main motivation for this study came from a paper published by Ortiz-Suslow et al. In 2019. So this was really interesting because this was the first results documenting the impact internal waves can have on the atmosphere. So this was an experiment done with FLIP off the California coast, and they deployed an air-sea interaction mast with a mounted field camera, and they found that the air-sea momentum flux was enhanced over these internal wave packets. So this figure over here shows the momentum flux, and these vertical dotted lines represent the arrival of the internal wave fronts. And they actually saw about a 90% increase when compared to immediately before the event, and about a 62% increase compared to immediately after the event passed. So a pretty noticeable enhancement of momentum flux associated with these internal waves passing through FLIP. It's important to note that this study considered a large vertical profile, so they looked at multiple levels above the surface in this experiment. And from this, they suggest that these dynamics should be considered in fine scale ocean studies. This is the internal wave. So this leads me to my question: do internal waves impact momentum flux like what Ortiz-Suslow et al. Is suggesting? And if so, what's the significance? Are they really enhancing momentum flux, or is there some sort of redistribution of energy? And if there is an enhancement, should we be incorporating these into our understanding of air-sea interaction dynamics and the numerical modeling of these processes? So the coastal land air-sea interaction experiment is actually an ongoing experiment that I've been involved in over the past couple of years. So the first couple of fielding campaigns took place in Monterey Bay, California in 2021, which had 2 legs of the experiment, and then again in 2022, both in the summer months from June to October about, and now it's being done in Pensacola. So the idea behind this project is to use this comprehensive data set we're acquiring to develop a new wind field model that better represents the physics of these coastal regions at the land-sea boundary. So waves and wind behave very differently in coastal regions than compared to the open ocean. So we want to kind of fill the gap of this lack of measurements by collecting air-sea interaction measurements in these regions. So we chose Monterey Bay for its diverse coastal topography and high wind wave action. And then we have Pensacola as a contrasting location with a different, less mountainous coast, more sand-based at a different time of year. So Monterey Bay, we deployed 5 ASIS buoys, which I'll explain more what those are in the next slide. So, but this is what an ASIS buoy looks like, and that's me out in Monterey Bay. And these were the locations of the buoys during the second leg of the experiment that I'll be talking about today. And we also have QT ASIS buoys, which are ASIS buoys, but just equipped with some additional instrumentation related to another collaborating institution on this project. So in addition, although this project was not designed to look at internal waves, Monterey Bay is home to the largest submarine canyon on the west coast of the United States, which creates this complex internal wave environment. So from the STAR images, we can see that there's a lot of internal wave activity over the course of this experiment, and this is due to the submarine canyon, as I mentioned, how internal waves form, and propagate across the continental shelf. The same is true for propagating over the submarine canyon. So with that, I will move on to explaining the ASIS buoys. So these are called Air-Sea Interaction Spar buoys, which was developed by Graeber et al. In the early 2000s to enhance the measurement capabilities for studies pertaining to air-sea interactions. They wanted to surpass the existing constraints of high-resolution measurements of waves and atmospheric surface fluxes. This was a notable advancement back when these were developed. So it's a pretty interesting platform. So this is what it looks like going into the water here. It's much larger than it appears at the surface. So this is a stable platform with low flow disturbance characteristics on both the air and the water side of the boundary layer, which is required to attain these measurements of atmospheric surface fluxes close to the surface. So this can be equipped with a lot of instrumentation, specifically what I'll be talking about today with wave wires. We have an array of wave wires on here, which allows us to look at the wave elevation as well as calculate directional wave spectra due to the array of the wave wires. We also have sonic anemometers mounted on the tower portion of ASIS on the atmospheric side, and this is what I mentioned can give us the 3 components of wind velocity. In addition, we also have motion packages on the buoy, because in order to convert the buoy's motion to actual Earth reference coordinates, we need to know how the buoy is moving. And we have a tether buoy attached, which helps prevent additional downward force because this buoy is actually attached to a subsurface mooring. This was actually, this experiment was the largest deployment, I believe, of the ASIS buoys to date, since we deployed 8 ASIS buoys. In addition to the ASIS buoys, we also had, I said, SAR imagery, as well as this X-band marine radar tower. So this tower was located at this station down here in the Pacific Grove area, and the reason I chose to use this is it actually has an ASIS buoy called Romeo, because it's the red ASIS buoy, and this is the ASIS buoy I'll be considering in my analysis today. And this marine radar swath is about 3 kilometers in radius and has the same imaging principles as SAR. Now I'm going to discuss my methods. So I have 2 different types of sensors I'm considering. So I have my ASIS buoy as well as my marine radar. And from the ASIS buoy, I'm able to estimate the turbulent fluctuations of wind velocity and the product terms, so from the 3 components. The marine radar gives me knowledge that there's an internal wave event at the ASIS buoy. So I'm able to estimate the duration of the internal wave event at the ASIS buoy, as well as calculate the wave period and frequency. I'll apply the Morley wavelet transform, which I will talk about in more detail in a couple slides, but basically this gives me a representation in both time and frequency to look at the evolution of features over time. So from these wavelet plots, I'm going to be looking for enhanced energy at or near the frequency of the internal waves that they're propagating near the time they're arriving at ASIS. And from that, I'm going to assess the contribution to the total flux, assuming I'm seeing this internal wave frequency in the wavelet plots, by taking the cumulative sum of the co-spectrum. This methodology was inspired by a study on the effects of roll vortices on turbulent fluxes in the hurricane boundary layer. So this study actually used SAR data as well as in situ measurements to quantify the roll contribution to the total air-sea transport of momentum and heat. So I was trying to see how I could use this to relate what I have with the marine radar to this in situ measurements and combine my measurements to draw a conclusion about how the internal waves are affecting the total transport of momentum. So from this study, they had SAR imagery that gave them the wavelength of the rolls, which was about 900 meters, and this corresponded to a frequency of about 0.13 hertz. And in the cross roll band, this had a dominant spike in the momentum, heat, and humidity fluxes at that particular frequency. And from the wavelet plots, we can see that there is a lot of enhanced energy at that particular frequency for the crosswind legs compared to the long wind. There's still some present in the long wind, but they're not as dominant as what you see in the crosswind. And from this, we can determine that what we're seeing in the data is related to the roll. So this plot is going to become important later, and I just wanted to give an example of what I'm looking for. So the top plot is an example of the cumulative sum of the co-spectrum from the high to low frequencies, which gives me an estimate of the total momentum flux in the top plot and the total heat flux. So the solid line represents the crosswind roll, where we're seeing this spike in the frequency related to the roll vortice, whereas along the dotted lines are all long wind legs, which don't have this same contribution from the frequency of the roll. So there's a narrow band and a lot of energy concentrated in the narrow band of the roll frequency in both these plots, but the result is different. So the mean of the long wind rolls is about 50% lower than what we're seeing from the crosswind roll, indicating that there's an enhancement of momentum flux. Whereas in the heat, that's not necessarily the case. This solid line curve falls pretty close to in the middle of all the long wind cases, indicating that this contribution from the roll isn't really enhancing the overall heat flux, it's more redistributing energy. Whereas with momentum, the rolls are actually playing a role in the enhancement of momentum flux. So I'm going to be looking at doing a similar kind of analysis with curves like these and seeing if the internal waves actually, I'm seeing the enhancement like what Dave saw, or if I'm seeing more of a redistribution of what they saw with the heat fluxes. So I have two case studies I'm going to talk about in detail, and we'll see what the results are from these two internal wave events. So I have a video. So you can see the internal wave, the alternating bands are bright dark as it propagates through ASIS. So this is just a video created from the time series, like a time series of images, which allows me, so I'll play it one more time, to estimate when the wave packet is propagating through ASIS, know when it's departed ASIS, and as well as estimate the period of the wave which I can then estimate the frequency I'm looking for in these plots. So this is the first case. The wave direction is propagating about the same direction as the wind, which is we want the wind to be propagating across the internal wavefront rather than along. Otherwise, we don't really see the same sort of response in the atmosphere. But the period in this case is about 8 to 9 minutes, which corresponds to a internal wave frequency of about 0.002 hertz. And this event took place from about 2220 to about 2400 UTC. If you notice, there's a pretty large shift in wind direction at the beginning of the event. It's almost like a wind turning event. And we didn't want this to contribute to what we're seeing on the atmospheric side. So we actually just isolated out those first 10 minutes of the internal wave event. So we could say we weren't seeing contributions from this wind shift as opposed to just the internal wave event. Because you want relatively stationary wind conditions, so the speed isn't changing much. These are 2-minute averages. It's about 4.5 to 5 meters per second, reasonably strong winds, and the wind is shifting slowly, but only about 20-30 degrees. So in some cases, this isn't very stationary, and it makes this kind of analysis difficult. So if we look at the power spectrum of the 3 components of the wind velocity and the product terms, we see a lot of spectral energy and the V component, which is corresponding to the direction of propagation of the internal wave. Not so much in U or W, and a little peak in the VW, which at about the frequency the internal wave is propagating. So now back to the Morley wavelet transform. So if you're not familiar with wavelets, it's a cousin of the Fourier transform, and a Morley wavelet is just a type of wavelet. There's different types. It's just the one I selected based on its performance in the past on decomposing geophysical time series. So the Fourier transform only gives me information about the peak frequency I'm seeing in a time series, whereas a wavelet actually gives me information in the time domain as well as the frequency domain, which makes this advantageous for non-stationary analysis. And because I'm concerned with when this frequency is occurring in time, I don't want to just know that, oh, that frequency is there. I want to know when it's appearing. So this is the shape of a wavelet. So compared to the typical Fourier transform, where you have a continuous sine wave you're convolving with a time series signal, we have a sine wave in a Gaussian envelope. So basically, this wavelet is translated along a time series, which is the component that gives us the temporal or the time information. And we can track the wavelet, which, as we move it along the time series, which gives us the frequency information. So from this, we can get a scale time representation of a 1D time series and look at how the energy is being represented at the particular frequencies as well as when in time. So just for a visual comparison, so the bottom is an example of a wavelet plot for the time between 1800 and 2400 UTC, whereas we see that there's peaks in frequency, but I don't know when in that 6-hour time frame these peaks are occurring, and the internal wave is not present in the entire 6 hours. I want to know when this energy is being concentrated. So from the wavelet, I can tell, oh, from the early period of this time series, there's no peaks in that frequency that I'm looking for at the internal wave. So that's why I chose to use the wavelet analysis and how it's different than the Fourier. So that takes me to my results from the wavelet transform. So there's a lot going on here, but the top plot is the U component, the middle plot is the V component, and the bottom plot is the vertical W component. So as I saw earlier in the power spectrum, I saw a noticeable peak in the V direction, so it's not surprising that I see an enhancement of energy as well at that particular frequency. There is some a lower magnitude enhanced energy in U, but it's nothing compared to the dominant signal we're seeing in V during the internal wave event, which is occurring between these two black vertical lines. So if we look at V a little closer, I wanted to know, is this some sort of energy that appears every couple hours at ASIS, or is this unique to the internal wave event? So from the 6 hours before the internal wave event in V, there's nothing at that frequency of that magnitude, and same with the 6 hours after. So I know this enhanced energy appears at the internal wave frequency, and it also disappears as the internal wave passes. So I mentioned earlier that I'm going to assess the contribution of these internal waves to the total momentum flux, and how I'm going to do this is I take the cumulative sum of the co-spectrum, so the co-spectrum of UW and VW, so these curves from the high to low frequencies, so I'm summing up from this direction. And I do this for the co-spectrum for before the internal wave event, the hour and a half before, the hour and a half duration of the event, which you can see here is the spike that I've been seeing in the V component, and as well as the hour and a half after the event, to compare and see if I'm seeing this enhancement or a redistribution of energy. So that takes us to these cumulative sum curves. So the top plot is showing U. There's really no narrow band of frequency in the internal wave and U, with the red curve in both cases being the internal wave event, the dashed dot being before, and the dashed dash being after. So if we take a look at V, we see that there is a very narrow frequency band, which represents a lot of the energy is from the internal waves. But we're not, yes, it's enhanced a little bit, but it's nothing like what we were seeing in the roll vortices in terms of magnitude. So we know the internal waves are playing a dominant role to the total momentum flux, but it is not showing a noticeable enhancement compared to before and after the event. But this is just one case, but from our initial observations, we're suggesting that internal waves don't really enhance the momentum flux, at least in our case, but they're redistributing this energy from the flux to other scales. But that's one case, so we decided to take a look at a second case. We have similar type of analysis. So this is a similar case with the wave direction being about the same direction as the mean wind. We have a slightly lower wave period, 6 to 8 minutes, which gives us more of a range of frequencies between 0.002 and a little higher, under 0.003. This was a less defined internal wave event in terms of a radar signature. So it was a less strong surface modulation, at least in this case. But the internal wave took place from about 0:40 to 3 UTC. The conditions were pretty stationary during this period, with a pretty constant wind speed as well as direction over the course of the whole internal wave event. So again, if we look at the power spectrum, we see a dominant peak, an even higher magnitude peak than what we were seeing in the V component, and a little peak in the VW. Again, nothing notable really in the U component. Yeah, the peak frequency. This was a little different than what we saw in the first case study. So you actually see two pockets of enhanced energy, which I attribute to possibly being related to the varying period of the internal wave, because this would correspond to closer to a 6-minute period, whereas this would correspond to closer to the 8-minute period that we're seeing. But there is dominant enhanced energy in the B component during the time of the internal wave event, with the higher magnitude being closer to the period that I would expect. If we look at V again, before and after the event, we have nothing of that magnitude before the event, and again, nothing after the event. It's very localized to the internal wave event. So now taking a look at these cumulative sum plots again. So this looks a bit different than what we saw in the past plot. This has, again, narrow band of frequency concentrated at the internal wave frequency, about 0.002 hertz. Again, you're not seeing this really mu. You see a little bit of a curve, but nothing compared to what we're seeing in B. And again, the total of this curve, it falls between that after and before events. It's really not an enhancement compared to the periods around it. So from this, I would say that supports my belief that this is redistributing energy. It's not a noticeable enhancement, at least in this case. But there is a narrow frequency band around 10 to the minus 1 here, which is just the peak in the wave spectrum. So this is from the wave energy is what we're seeing here, which the internal waves aren't contributing any more than what we're seeing from the surface wave energy. I'm going to talk about some other types of analysis I did that were just supplemental, as well as some other internal wave events, and as to why I didn't do any further analysis on those in terms of what was going on in the atmosphere with wind conditions that made it difficult. So this was the case this was my first case. So again, I have my internal wave event, which I isolated out. But I presented earlier that we have this well-known relationship between internal waves and how they modulate the surface currents, and how these internal waves play a large role in what we're seeing at the surface. But this is usually not the focus of an in situ study of internal waves experiments, because we're more concerned about what's happening under the surface. We're not really concerned about what's happening with the surface roughness. And since on ASIS we have these wave wires, I wanted to see if I could actually resolve the surface roughness variations of these small short surface waves with the center wave wire, which I was actually able to do. So this is the internal wave events. The magenta lines are the bright radar signatures, arrivals, and the blue is the dark radar signatures. And this is just the standard deviation of the wave elevation, and it's bandpass for the 1 to 7 hertz waves. So I'm specifically looking for the short wave variation. And it's not perfect, but you do see pretty constant higher elevation waves associated with the bright arrival of the radar signature, which was kind of interesting to me from a remote sensing perspective. And I did this independently of looking at the curve. I just wrote down the times and plotted them. And I was kind of surprised I was actually able to resolve the short waves with the wave wires. I wasn't sure if we'd be able to do that. So another case, which this one looked promising from a radar perspective. It had a very strong surface signature. You see these clear, bright, and dark bands, much more so than in the second case I showed. But this case has a very large shift in wind direction over the duration of the event, almost 100-degree wind shift. The wind speed's fairly constant, but the wind speed is shifting a lot, which makes it hard to determine what's related to the internal wave, what's just related to the atmospheric wind shifts. And the wind wasn't quite, it had some more along frontal components in this case than the other ones with the cross frontal. And there also was maybe another internal wave event, which looks like it from the radar, but I can't be certain without a subsurface temperature measurement. But I did do the roughness analysis on this to see if I just got lucky with the first analysis of the surface roughness, but I did see the same relationship with the arrival of the bright radar signature and the sharp drop off of the dark, especially at the beginning of the event. So this was kind of an interesting finding, or not finding, but an interesting observation from byproduct from this project. And finally, I have this other case here, which I have again a pretty clear internal wave event approaching the ASIS buoy. But during the internal wave event, the wind is doing all kinds of different stuff. So the wind speed is dropping almost down to close to zero, so basically no wind, which when there's very low winds with ASIS, it tends to drift more with the surface currents than be moved by the wind. And that makes it hard for us to correct the ASIS's motion to the motion package data as accurately, because ASIS is kind of sometimes just spinning, or you get more of like a pseudo swirling wind, which we're seeing a lot down here. The wind speed is just all over the place, which when the winds are too low, we can't really, again, do this kind of analysis very well. It makes it very challenging. So, well, I showed 2 case studies. We do have more cases, but the atmosphere isn't necessarily cooperating in the way that I can do the type of analysis that at least I did to relate the internal wave to this radar signature and link it to what's going on with the winds. I originally started out doing this with the SAR data rather than the marine radar, because my previous work had been with SAR, but SAR only gives me a snapshot in every 6 hours or however many hours between satellite acquisitions. But the wave moves a lot in that period, and then I was trying to estimate when the wave was passing through ASIS, and that wasn't really giving me a good period estimate, and I didn't really know when and how long the wave was actually at the buoy, which brought me to the marine radar station, which actually, the way the station was located further south in the bay, we were able to get more situations where we had the wind blowing in the same direction as the internal wave was propagating, rather than directly along the internal wave crest. So the marine radar definitely played an important role in me being able to estimate the frequency of the internal wave and the duration of the event accurately when compared to SAR. So now some conclusions and takeaways from this talk. So as I showed, in both cases, we do have a narrow internal wave frequency band where a lot of the energy is concentrated and contributed from the internal wave between V and W, but based on the 2 case studies, we believe that these internal waves are redistributing the momentum flux among other scales, which is contradictory to the noticeable enhancement that Ortiz-Seslo et al. Saw in their case study. Their case study was, again, very different in terms of they looked at several points above the surface, whereas I only had one sonic anemometer, whereas they had from 0 to 15 meters above the surface. So maybe that played a role in some enhancements they were seeing at higher altitudes. I'm not sure, but they also approached it a little bit differently and had subsurface sensors as well in terms of what was going on the ocean side. It's important that the wind is blowing in the same direction, so across the front of the internal wave, to see this sort of response. And it's also important that these waves are stationary during the internal wave event in order to be able to relate this to an atmospheric response and isolate it from other possible atmospheric events occurring. And again, compared to what Dave saw, we both saw kind of different results, but further research is required to understand how this could implicate numerical modeling and the mechanism that it's kind of how it's working. Yes, we know there's some sort of interaction occurring, but exactly what is causing it would require further research. It would be interesting to look at an ASIS buoy if it had a subsurface temperature mooring to see what was going on also below the surface. I know we do have some of that from the Classy project, but we don't have it in the swath of the marine radar. But it's definitely an interesting problem that's very complicated to unpack. But I think it's pretty cool to look at internal waves from a different perspective. And I just wanted to acknowledge everyone I worked with in this project, that Dave Ortiz for helping give me the idea to look into this a bit further. And I actually got, unlike my first project I worked on here, I got a very hands-on experience with the ASIS buoys. I helped build them, I helped mount instruments, I helped break them down, I helped deploy them and recover them. So that was a very cool experience. And these are just some pictures from my experience with the project. And with that, thank you. And let me know if you have any questions. Any questions from the room?
No questions from all the people here in the room audience. Do we have questions from the Zoom audience?
Hey, Sam, Dave Ortiz also here.
Yes.
Great talk. It was cool to see the results of your work.
Mm-hmm.
I had a kind of a very basic question going back to the plots of wind direction.
Yes.
Well, I had a couple questions about the wind direction, but my first one was pretty basic. I noticed that you can go back to a couple slides ahead of this one. So some of your wind directions are above 360
Yes.
degrees.
Yeah, so I just added 360 to anything that fell below 100 degrees, so it wasn't kind of having this 0 to 360 spikes that look like a
Okay.
really large wind shift, but aren't.
Okay.
Yeah, so this
That's
is,
what I kind of figured. I just wanted to double check.
yeah.
Okay. And then I was kind of curious. So, given the radar maps you have, it seems like you can estimate the internal wave propagation direction very well.
Mhm.
Did you consider rotating the local winds from ASIS into the propagation direction so you can look directly at the
Yes.
cross-frontal component versus the along-frontal component?
So I've just started thinking about that, and that's probably something I'll end up doing for my next step, honestly, and final
Yeah.
kind of tying together this work, because I know that's commonly, I believe that's what you did in your paper, I think, with the cross.
No, I didn't rotate in the propagation direction because I didn't have as good of maps as you as
Yeah.
estimating. I just only could use cases. I could only use a case when I knew the wind was cross frontal.
Mhm. Okay.
But
yeah.
in this case, you might be able to look at it.
Yes.
You might be able to do that rotation. It might pop out the signal a bit more.
Yeah. That's a good idea, and that's definitely something I've considered, but I hadn't gotten to yet. But thank you.
Yeah. No, I mean it's cool to see. It is a very different regime than the previous study. Your wind speeds are also much higher, so you would expect the atmospheric signal to really dominate. So to be able to tease out any internal wave signal from this is actually kind of interesting.
Mm-hmm. Yeah, it definitely was a kind of finding cases that were cross-frontal and not too low wind speed, but also not too high wind speed. It's definitely not an easy problem, but it's very interesting, and I think it's interesting that we're seeing stuff contributing from these lower frequencies too, that you typically would maybe just think is more noise too. But.
I have a question too.
Yes, go ahead.
Yeah, so hi Sam, that was a nice talk. So real quick about your first case, I think in your wavelet diagrams, I think I saw an internal wave, so like enhanced energy or an internal wave signal before you actually saw the internal wave.
Yes.
So
let me just go back here. Yeah. So I believe this could be due to potentially the wind is moving faster than the internal wave is propagating, so the atmospheric signal could arrive a bit ahead of the actual internal wave event. And it's also, these radar signatures are just modulations of the internal wave, so the exact arrival of the internal wave could be offset a little bit. But I think it's more likely the wind's signature could just be arriving a bit earlier than what we're seeing.
Yeah, I think so. Yeah, my thought is, yeah, that's what I had in mind too, and I would think that the radar, the enhanced radar backscatter should actually closely correlate with, the enhanced roughness that your wind measurements respond to. But yeah, so maybe it's an upstream signal of the internal wave that you just detect sooner.
Which I do.
But yeah, that kind of that struck my interest. But otherwise, yeah, really nice talk.
Thank you.
Okay, do we have any further questions from the Zoom audience? If not, I think we can thank our speaker again. And I thank all of you for coming today and
Yes, thank you,
in the
everyone,
room
for-
and in Zoom. There will
Attending.
be no seminar this Friday, if I remember that correctly, and there will be no seminar next Wednesday, but we will continue next Friday with an invited speaker, if I remember that correctly. Watch the emails.